All right, let's talk about something absolutely wild. We're going to tackle a huge question, maybe one of the most fundamental questions in all of physics. It's a mystery that's hidden inside every single atom. You know, the stuff that makes up everything. So let's get right into it.
I know, it sounds a little dramatic, right? Why doesn't the universe just collapse? But here's the crazy part. Based on everything we thought we knew about physics, say back in the 19th century, it absolutely should. If atoms played by the classical rules, the rules of electricity and magnetism that we trusted, they'd be completely unstable.
So you've got this massive clash. On one side, the prediction from all the best physics of the day says that electrons should just radiate away all their energy and spiral into the nucleus in, like a fraction of a second. Instant collapse. But then, you look around, and the observed reality is that atoms are incredibly stable. They're the building blocks of everything. Clearly, something was deeply, fundamentally wrong with how we understood the universe.
Okay, so this was a real crisis for physics. To try and get their heads around it, they came up with this picture of the atom as a tiny little solar system. You've got the nucleus as the sun and the electron as a planet zipping around it. It's a cute picture and it kind of helps, but it has a huge fatal flaw. And that flaw is really the heart of the whole problem.
See, according to classical physics, any charge that's accelerating has to give off radiation and lose energy. It's just a rule. And the key word there is accelerating. Now, you probably think of acceleration as just speeding up, right? But in physics, it also means changing direction. And what's an electron doing when it's orbiting? It's constantly changing direction. That means it's constantly accelerating. So according to the rules, it should be constantly bleeding energy, which would send it on a death spiral right into the nucleus.
So things looked pretty bleak for the atom. Then along comes the Danish physicist Niels Bohr. And he was the first person to really look at this classical picture and say, you know what, maybe the rules are just different down here. He didn't have the whole story, not by a long shot, but he proposed some seriously bold, radical new rules for how atoms work. Okay, so Bohr's idea was basically this. Think of an energy ladder. He said electrons can only live on specific rungs of this ladder, these stationary states. They can jump up a rung or fall down a rung, but they can't hover in the space between the rungs. And here's the most important part. As long as an electron is just sitting on one of its allowed rungs, it just doesn't radiate energy. The old rules don't apply. And this idea worked amazingly well for hydrogen. But it didn't explain why. Why these specific rules? It was a fantastic clue, but it wasn't the final answer.
To really get to the bottom of this, we have to do something kinda drastic. We have to take that little solar system model and just throw it out completely. Bohr's rules were great, but they felt a bit arbitrary, like he just made them up to fit the data. To figure out the why, scientists like Erwin Schrödinger had to ask a much deeper question. What even is an electron? And trust me, this is where things get really, really strange.
So, first things first, we have to stop picturing the electron as a tiny little ball zipping around in a circle. It's not. Instead, quantum mechanics tells us to think about it using something called a wave function, and you can basically picture that as a probability cloud.
And this is a huge mental leap. The electron isn't in one spot. It has a chance of being in many places all at once, smeared out in this cloud around the nucleus. It's not orbiting the nucleus. In a way, it is the orbit. This cloud has a very specific shape and, crucially, a lowest possible energy level, its ground state. And once it's in that state, it just can't lose any more energy. It has nowhere lower to go. But there's still one final piece to this whole puzzle.
All right, the final nail in the coffin for the whole collapsing atom idea. This comes from Werner Heisenberg and his famous uncertainty principle. And this isn't just some clever theory. It's a fundamental, unbreakable law of the universe. It's what provides the ultimate quantum shield for the atom. So what does it say? It's basically a cosmic trade-off. It says you can never, ever know both the precise position and the precise momentum of a particle at the exact same time. Momentum is just its mass times its velocity. You can think of it as how much oomph it has. The more you pin down where something is, the less you know about its oomph. And the more you know about its oomph, the less you know about where it is. They're connected at a deep, fundamental level.
So let's run a little thought experiment. What if we could somehow grab an electron and try to force it to squeeze it right into the nucleus? What are we doing there? We're trying to make its position incredibly precise. So what does the uncertainty principle say is going to happen?
Well, the universe pushes back. The uncertainty principle kicks in, and it kicks in hard. The more you try to squeeze that electron, the more you pinpoint its location, the more its momentum goes absolutely haywire.
it becomes wildly, massively uncertain. It would start to jiggle and vibrate with a tremendous amount of energy.
Heisenberg himself put it perfectly. The more you nail down the position, the less you know about the momentum, and vice versa. And it's so important to get this. This isn't because our instruments aren't good enough. It's not a measurement problem. It's a fundamental feature of reality itself. The universe just has a built-in level of fuzziness.
And that right there is the punchline. The very act of trying to shove that electron into the nucleus gives it such an insane kick of energy that it would just instantly shoot right back out. It's like trying to push a super bouncy ball into a tiny crack. Nature literally forbids the atom from collapsing because the energy price is just way too high. The electron finds its stability, its lowest energy state, by being spread out and, well, uncertain.
So there we have it. The puzzle is solved. But this isn't just some abstract little problem for physicists to argue about in a classroom. The stability of the atom, this quantum shield, is the reason that, well, everything exists the way it does.
No, seriously, this isn't just a theory. It's the reason anything is solid. Every object you can touch, every chemical reaction, every single process happening in your body right now, it all depends on atoms being stable, reliable building blocks. This quantum weirdness is literally the foundation of our reality.
And get this, understanding this quantum shield isn't just for explaining why your desk is solid. It's how we built the entire modern world. Think about the computer or phone you're using right now. The semiconductors inside, the transistors, they work by precisely controlling how electrons jump between those stable energy levels we mentioned. And lasers? A laser is just a whole bunch of electrons dropping from one stable state to a lower one, all at the same time, perfectly in sync. Pretty much all the tech we rely on is built on top of this one fundamental quantum rule. So when you boil it all down, the atom is basically in a perfect, delicate balance. It's a cosmic tug-of-war. You've got the classic electrical force pulling the electron in, trying to make it collapse, but fighting back is the uncertainty principle, creating this powerful outward push, this quantum kinetic energy that refuses to be pinned down. The result? A stable, predictable atom, the building block of our universe.
So just think about that for a second. The solid, predictable, reliable world that we experience every day is built on a bedrock of pure chance, probability, and fundamental uncertainty. If something so concrete and real can emerge from something so bizarre and counterintuitive, it really makes you wonder, doesn't it? What else is possible?